going to analyze a system where we have two blocks that are coupled by a string. One of the blocks is on a ramp and the other one is hanging over a pulley. We'll look at both situations where there's friction between the block on the ramp and no friction. So we'll start with a problem statement where we're on a frictionless ramp. The block of mass m is on a frictionless ramp of angle theta. Block is connected to a hanging block of mass m by a massless inelastic string over a frictionless massless pulley. Find the acceleration of the hanging mass. The process we'll follow is similar to what we've done for other force problems. We'll state our assumptions, find our known and unknown variables. We'll start by drawing free body diagrams, use the diagrams to construct equations, and then solve the system of equations for unknowns in terms of given variables. Then we'll do some analysis on our results. To begin with, for our system that doesn't have any friction, the first three assumptions were given in the problem statement. No friction, string is massless and inelastic, the pulley is massless and frictionless. The other three assumptions will add that the masses are point particles, and there's constant gravitational acceleration little g. That means we're close to the surface of the Earth. Also, we're not considering that there's any air resistance. We've listed our knowns as the two masses and the angle, and what we're looking for is the acceleration. We take our net force equation for the small hanging block. Net force in the y direction equals ma equals t minus mg. Notice we have our tension vector longer than the mg vector. That allows us to solve for tension equals ma plus mg. For the block on the ramp, we'll start with the net force equation in the y direction. The net force in the y direction equals 0 because there's no acceleration perpendicular to the ramp. The normal force is pointing upward, and the cosine theta component of mg is pointing downward along the y-axis. So 0 equals normal force minus mg cosine theta. For the x component, we have that the sum of forces in the x direction equals ma. There is acceleration along the ramp. We have downward along the x-axis is positive, so our mg sine theta term is positive, and the tension is negative. So we have capital Ma equals capital Mg sine theta minus T. We can use our equation for the hanging block to substitute in for the tension term. And then we can sort off our acceleration terms to the left side of the equal sign. Now we can solve for our acceleration. A equals capital M sine theta minus little m multiplied by g divided by the sum of the masses. We can do a little bit of analysis here. We see that if we let little m go to 0, our acceleration equals g sine theta, like we would expect for a block accelerating down a ramp. Also, if we let capital M go to 0, we get a equals negative g. The little block would just be in free fall. Now let's look at our analysis if we decided to put the acceleration in the opposite sense, with the small block accelerating downward and the large block accelerating up the ramp. We've switched the direction of the y-axis for the small falling block and the x-axis for the block on the ramp, and notice that for the block that is falling, we now have mg larger than tension. We can take the net force in the y direction equals ma, and now we have mg minus t, which gives us tension equals mg minus ma. For the block on the ramp, the y component is just the same as it was before, n minus mg cosine theta. For the x component, we have capital Ma equals tension minus mg sine theta. We can do our analysis like we did before, substituting in for the tension and then sorting off the acceleration to get an expression for our acceleration. When we compare it to what we got before, which I've shown in blue here, we can see that the magnitude is the same and the direction is opposite. Now let's do an analysis adding friction between the block and the ramp. Our equation of motion for the hanging block doesn't change, and neither does the y component equation for our large mass. Our net force equation for the block in the x direction down the ramp will change, however. Here you can see we've added the friction force, mu k times the normal force, and we've also added the friction force upward along the ramp, since in this estimation we're assuming that the acceleration of the large block is downward along the ramp. We proceed as we did before, just including that other friction force term, and that allows us to find an expression for the acceleration including friction. Now let's look at the case where we've changed the direction of acceleration to where the block is actually sliding up the ramp. This is quite different since the tension force and the friction force are now pointing in opposite directions. We follow through with the math the same way we did before. Notice we have the acceleration in the downward direction for the hanging block, the acceleration in the upward direction along the block for the sliding mass. The friction force is downward, so it's negative in our equations. Following through the equations, we can find an expression for our acceleration, including friction, for this case. When we compare it with what we got before, we see that there's something different. So for what we found just now, the m sine theta and the mu k sine theta term have opposite signs. What we saw before was that those two terms had the same sign. This gives different values to the magnitudes of the accelerations for the different cases. So in conclusion, what we did here was we considered a system of a block on a ramp connected to a small hanging block by a rope strung over a pulley. We used the force approach. We made assumptions, drew free body diagrams, took equations from the diagrams, and then solved these equations, analyzed our results for the case of no friction and for friction. What we found for with no friction, taking a guess as to whether our acceleration was down the ramp for the sliding block or up the ramp, the magnitude of acceleration was independent of the direction of motion. For the friction case, the magnitude of acceleration did change depending on what we chose for the direction of motion. Thank you very much. Please come back again soon.